Okay, let's suppose that we have a quadratic, something that we think is going to be quadratic in nature, a function that's going to be quadratic in nature. And we think that its vertex should be at 80, 0, or we know maybe that its vertex should be at 80, 0, and that f of 0 is 200. Okay, well, to represent this function, we can construct a graph. So I'm going to attempt to draw a parabola. And it's probably not very good freehand drawing a parabola. I'd been better off if I'd have started with the vertex, moved over 1 unit, up 1 unit, moved over another unit, and up 4 units. And I can see already that this isn't a very good parabola. Now, if you do this as a homework problem or as a test problem, you probably want to be careful to construct a good parabola. But right now, I don't particularly care if it's a good parabola or not. I'm going to draw it, and then I'm going to test it to see if it's a good parabola, or at least talk about how to test it. Okay, so I can take any point on this. Well, first of all, I can take the vertex. We know that has to be here. So this point has to be 80, 0. Now, if f of 0 is 200, then I could take any point over here and say that this is the point 0, 200. Now the question is, where am I going to put my axes? Well, it's obvious that the x-axis has to go through the point 80, 0, because the y-coordinate there is 0. So I draw my x-axis here. And my y-axis has to go through the point 0, 200, because there x is 0. So now I know where my y-axis is, and I know where my x-axis is. I can also easily now make a scale. Okay, I can go to 80. I know that the x-coordinate here is 80, so that I'll just put an 80 there. If I go halfway back to the origin, that should be about here. Then I know the x-axis is going to, or the x-coordinate is going to be 40. If I come back to here, x-coordinate is going to be 20. Here it's going to be 60. And then I can subdivide those intervals without labeling them. And I get a reasonable approximation. For 0, 200, I can divide this in half, and the interval from 0 to 200. That's going to give me 100. I can divide this in half, and I'll get 50 down here. Divide this in half, I'll have 150. Of course, I've got 200 here. And then I can subdivide each of these intervals into 5 subintervals. Try to do that as accurately as possible. And I'm doing it by hand and by eye, so it's not going to be great. And my 0 to 100 is too big. I should have divided it down here. So there's a problem with my scale. So if I'm doing this, and I'm going to maybe do it, kind of play a game with it, see how accurate I can be, then I'm going to divide things up a little more carefully. But I'm just trying to illustrate right now, so we'll take what we have. Okay, so now I can start making estimates. Okay, I can estimate let's say the average rate of change of y with respect to x on various intervals. So let's say I want to do that on the interval 10, 30. On the interval 30, 50. On the interval 50, 70. It's easily done. When X is 10, I can project up to the axis, and it looks like I've got about 117 there. So it looks like I've got the point 10, 117. If I've got a really good graph, I might actually be close. Again, because of the fact that I didn't subdivide the arrow from 0 to 200 very well, and it's probably not very accurate, but we're making estimates. Okay, and then when X is 30, I have the point 30, looks like pretty close to 30, 40. Then when X is 50, I think I've got the point 50, 17. I like the sevens, but that's what I'm seeing. Okay, and then at 70, well, here's 70, and that's going to be down pretty close to the x-axis. I think I got it a little high here, so I'm going to fudge a little bit. Yes, I've got the point 70, 4. Okay, now all these points might or might not lie on a parabola. We could take any 3 of these points and obtain the equation for good parabola. And then we see if the 4th point lies on that parabola, or even more importantly, see if the vertex of that parabola really is at 80, 0, and the y-intercept really is at 200. I guarantee you with these points, it's not going to be all that close, but it might not be all that far. Okay, now we want to get the slopes because we want the average rates of change. The average rate of change, well, the change in y is the rise between 2 points, and the change in x is the run between 2 points. And the rate of change, average rate of change, is the change in y divided by the change in x. And that is identified with the slope. So we could think of line segment here from this point to this point. That'll be the line segment corresponding to the interval 10, 30. Then a line segment here and a line segment here. And we can, might as well make things colorful. We can sketch the rise and the run for this triangle, the rise and the run for this triangle, and the rise and the run for this final triangle. Can't really see where the arrows are on that triangle. And we determine then that what the rates of change are. Okay, the rate of change, and I'm not going to do that in detail. I assume everybody knows how to do that. The rate of change for this triangle is going to be what? Going to be negative 77 divided by 20. So the rate of change there, let's use even a different color. The rate of change, average rate of change for this triangle is negative 3.85. You can check my numbers. But there's the average rate of change on this interval. Yeah, I could be right or I could be wrong. It's negative 77 over 20. Pretty sure that's what comes out, okay? And here we have what? Negative 23 over 20. Okay, that'd be negative 1.15. So don't have room to squeeze that in, but we'll say that that applies to this triangle, and to this triangle, it's negative 13 over 20. That would be negative 0.65. Now I can tell from these numbers that I didn't do a very good parabola. Matter of fact, it's really a pretty bad parabola because the change in the slope from this interval to this interval should be the change, same as the change in slope from this interval to this interval. This is a parabola, that's going to be a property of it. It's not a property you're required to know. If I ask you to verify that, you would, we'd want you to do that. Now that applies if the intervals are consecutive and have the same length. And that's related to some of the things that you're asked to do on the take-home exam. Okay, so I wanted to illustrate, though, how we can take a sketch of a parabola and make it fit conditions like this. Gotta pause this thing and change the board. Okay, let's just take another, and we'll use a quadratic model. We have this information on a quadratic, and we're going to do something similar to what we just did. And I'm going to be a little more careful this time. I'm going to put a point here for my vertex. Of course, that's going to be 120, 50, so let's go ahead and just label that. And I'm not going to put axes down because that'll confuse me, because the axes for this function are not going to coincide with the axes for the basic function. But we come over some distance here and up the same distance and get a point on the parabola. And then if we come over the same distance to here, then up 4 times this distance, 1, 2, 3, 4, we're going to end up about here. Now, if I come over same distance I did before and up to here, and then come over that same distance and then up to here, I should get a better parabola than I did last time. And it's easy to do this. Okay. So now I can sketch. Still not going to win any prizes. Okay. But I'm going to at least made an attempt to get these things right and so forth. Okay. Now I can take any point and let that be the point 30, 140. I'm going to take this point here. I'm going to call that point don't really want to label it there. Okay, I'm going to label it here 30, 140. And my vertex, of course, is 120, 50. Now, where am I going to put my axes? My x-axis doesn't go through this vertex. My y-axis doesn't go through this point. Well, there are 2 things I can do. I can say, well, let's just subtract 30 from all the x coordinates and subtract 50 from all the y coordinates. And that'll give us the graph, this function's graph. Shifted 30 units this way, shifted 50 units this way. Find what we did want to find about that function, and then just shift those coordinates back. Add 50 to any x coordinate we get, add 30 to any y coordinate we get. That's perfectly legitimate. And of course, we could even shift it 50 units in the x direction. So the vertex is here. and figure out horizontal and vertical shifts. Okay, well, that's legal, but for the purposes of the questions that I'm asking on the take-home final, it's unnecessary. So what I'm going to do is I'm going to say, well, let's see. This x coordinate is 120, this x coordinate is 30. So how much further am I going to have to move my y-axis to fit all this information? Well, from 30 to 120, the horizontal distance from here over to here is 90. Okay, so if I have that distance, okay, this distance is, this is like 90. I take a third of that. So I divide that into a third and get a third here. Say, okay, a third of that is going to be about here. I go over that much further. And here's where my y-axis needs to be. In other words, now this distance should be 1/4 of the distance from here to here, because 30 is 1/4 of 120. I probably didn't do that very well. 1, 2, maybe I didn't do too badly. But there it is. There's an estimate of where the x-axis ought to go. And then from 140 down to 50, well, coincidentally, that's also 90, but that's not going to be very helpful. I could say, okay, this is 140. This is 50. Now that's 90 units from here to here. So I can try to divide this into thirds, which is a little harder than subdividing into halves. Okay, and depending on how accurate you want to be, you can figure out various strategies to do that, but I'm not expecting miracles in this. And okay, so this distance would be a distance of 30. So here's 50, here's 80, here's 110. So now I come down another 30, that should put me here. So that should be 20. And I come down another 30. Well, that's going to be -10. And of course, I want my x-axis to be at 0. Well, here's -20, here's -10. I divide this into thirds. And here's 0. And here's 10. And now my x-axis is going to be here. And now I've got a scale already pretty well built. I can subdivide these intervals then. I can divide this. I can divide this. I can divide this. I can divide this. And now I have units of 10 marked along this axis and on this axis. And here's 100. Yeah, here's 120. I can cut that in half to get 60. Halfway between here and here is going to be 90. Halfway between here and here is going to be 30. And I can subdivide these. I'm not doing it very carefully. That was really bad. But yeah, you can do it better. And now I can make estimates. Now, depending on the information I have for a parabola, if I have 3 points that lie in the parabola, I can use simultaneous equations to find the equation of the parabola. So I don't have 3 points, so I'm going to have to estimate. So I'm going to estimate this point. Okay, the point looks like it comes down here at about, oh, I don't know, we'll estimate it in a minute. I'm going to just say that, okay, that point looks like it's about 80, 70. Okay, so now the equation of this parabola is, and let me get a little more colorful here. Equation of the parabola is y equals ax squared plus bx plus c. Okay, well, the point 120/50 is on the parabola. So whatever A, B, and C are, it has to be so that 50 equals A times x squared, which is A times 120 squared then, plus B times 120 plus C. Okay, well, also the point 80/70 I'm not going to write it out like I wrote it out here because I don't have that much room. But the point 80/70 says that when x is 80, y is 70. So 70, which is y, has to equal A times 80 squared plus B times 80 plus C. And then 3140 implies that 140 equals A times 30 squared plus B times 30 plus C. Well, now I have three equations. In the parameters A, B, and C. I write that as a set of three simultaneous equations. And I'm going to write this equation with the right-hand side on the left and the left-hand side on the right. I'm going to switch sides. Also going to square 120 and put 120 squared in front of A rather than behind A. But it's very straightforward to see that this term becomes 14,400 A plus 120 B plus C equals 50. Okay. Now, what I'm saying on my screen doesn't make me that happy because I'm having trouble reading this. Still, you should understand what I just said. Just listen to what I said. It's very clear. And this equation, 80 squared is 6,400. And then you have 80 B and C, and that equals 70. And then we have 30 squared is 900 A plus, the video quality is so bad because apparently my computer, for some reason, has decided to use its camera instead of the default camera. Okay, so this ought to be a little easier to read. I'll put the other board up there too for reference. Okay, so anyhow, we get 900A here and 30B. Equals 140. Well, we can solve this equation. We get a number for A, we get a number for B, we get a number for C, and we plug them in here. And now we've got our quadratic function. So something else I believe you're asked to do. Now, if you want to get a good picture of these things, should be a lot clearer. And I have no idea why Zoom defaulted the way it did. But anyhow, there we have it. So here is our first model. And here's our second model. Those principles work with any of our basic functions or any other function you draw the shape of. As long as you have the shape of a parabola, the correct shape of a parabola, the function that you get here, if you've done everything else reasonably accurately, should then have a vertex at somewhere close to 120, 50. And maybe it'll be 130, 47, or maybe the 30, 140 point, when x is 3, maybe you're going to get 150 up here, and maybe even worse, but still everything should be in the ballpark if you drew a reasonably good parabola. And of course, it's legal to just trace a really good parabola. Now, you really want to make sure that your picture is big enough. You don't want to try to estimate these details in a little tiny parabola. You don't have room to label it, and you're not going to get good estimates. Okay, so you want to use a big graph. Then you want to do estimates and play the game. See how well it comes out. Even if you totally screw it up as far as estimates and so forth, if you follow the right procedures, that's what I'm really looking for. Although I really like to see accuracy, and it's more satisfying to you if you do achieve pretty good accuracy. But don't become despondent if you don't have wonderful accuracy in these. But the procedure and the process and the understanding that comes with it is our real goal here.